Yet again, CERN has made headlines. The esteemed Lab for Particle Physics has announced a rather striking discovery made by their Large Hadron Collider that could potentially alter our understanding of the universe. Scientists have revealed that these peculiar readings might signal the existence of extraterrestrial life in a parallel universe. In this video, we will examine the recently uncovered CERN revelation that could change everything. In a new experiment with the Large Hadron Collider, scientists observed something unusual with a particular kind of quark. Quarks are the building blocks of all matter and come in different types, referred to by physicists as flavors. Some of these so-called flavors are incredibly unstable and decay rapidly. The focus of this specific anomaly was the beauty quark, which has an average lifespan of 1.2 trillionths of a second. As it turns out, the quark's decay pattern was significantly different from what researchers had predicted based on the standard model. According to their expectations, when a beauty quark decays, it should be influenced by the weak force and transform into what is known as a lepton, a group of lighter particles, either an electron or a muon. The standard model predicts an equal 50-50th chance for both particles. However, the data from the Large Hadron Collider showed something strikingly different. The findings indicated that these quarks decayed into muons only 70% as frequently as they decayed into electrons. This was particularly noteworthy because electrons and muons are essentially mirror images of each other, with the only distinction being that the muon is over 200 times heavier. Despite this difference, it shouldn't affect the rate of decay. All forces within the standard model should act on these two particles with equal strength. Since beauty quarks decay through the weak force, both particles should result from the decay in equal numbers. There's only one way for this phenomenon to occur: if a new kind of particle which has never been observed before is involved in the process. Some experts have been led to speculate that new physics could be at play. A new force-carrying particle would mean fresh material for physics, which could expand the standard model and answer numerous unresolved questions. The possibility of new physics is exciting. Currently, we don't have many ways to test particles, so the standard model remains our best understanding of how the bizarre world of particles behaves. The standard model is a scientific framework that describes everything we know about the building blocks of the physical world with great precision. However, even with this high level of accuracy, physicists are well aware that the model is incomplete. Many pieces of the puzzle are still missing. Of the four fundamental forces, the standard model can describe three: the electromagnetic force, the strong force, and the weak force. However, it has no representation of gravity or any explanation for dark matter, the dominant form of matter in the universe. During recent tests, experts noticed an anomaly in the data they were analyzing, which didn't align with what is known within the standard model. While it's common to find results outside the model due to the sheer volume of data the LHC produces, this anomaly stood out. Scientists knew they needed to investigate this new phenomenon further. What could this new force possibly be? To explain this remarkable discovery, scientists have speculated that there may be a new fundamental particle, which they have named Z', a brand new force-carrying particle. Although this force is likely very weak, given that no traces of it have been found until now, experts believe it interacts with electrons and muons in different ways. However, the extent of its interactions with particles from the standard model remains a mystery for now. This could be the breakthrough physicists have been waiting for decades. If new force-carrying particles are discovered, physicists are hopeful that this revelation, once confirmed, could help unlock long-standing mysteries of the universe and answer age-old questions, such as what dark matter is, or elucidate the full role of the Higgs boson in the creation of our universe. Some researchers have proposed that this unknown force could help achieve one of physics' most elusive goals over the past century: unifying the fundamental forces of nature. The Large Hadron Collider, LHC, excels in this area. Despite its capabilities, it only accelerates beams of particles, particularly lead ions, for 1 month each year. The primary goal of the LHC is to allow physicists to test predictions of various particle physics theories. Notably, they are searching for a wide range of new particles predicted by subatomic particle theory and measuring the properties of the Higgs boson. Composite particles consisting of quarks bound together by the strong force, much like how the electromagnetic force holds atoms and molecules together, are well-known hadrons such as protons and neutrons. The pion and kaon mesons, first identified during cosmic ray experiments in the late 1940s and early 1950s, are also included. The LHC brings two opposing beams of particles together to collide. When these particle collisions occur, they result in a shower of particles zooming out in various directions. These particles have an incredibly short lifespan, existing for only a fraction of a second or millisecond before decaying into nothingness. By varying the types of particles involved, scientists can detect new particles in these showers with the help of specially designed technology. Exceptionally sensitive detectors are placed around the collision regions to ensure no data is lost from each impact. This massive amount of data requires significant time and effort to sift through. The experiments at the LHC can generate over 15 petabytes of raw data from these collisions every year, which scientists then meticulously analyze to find the information they are searching for. The LHC reached a critical milestone in 2017 when scientists permanently archived over 200 petabytes of data into its tape libraries. To put this enormous amount of data into perspective, 1 petabyte is equivalent to around 250,000 movies. The Higgs boson is thought to be an elementary particle associated with the Higgs field, which is the quantum excitation of this field. It's akin to the way you see ripples in the ocean. The Higgs boson is like a completely new kind of creature in the zoo of particles. It has neither the quantum properties of elementary matter nor those of the carriers of quantum interactions, like electromagnetic, weak, or nuclear forces. The Higgs boson was discovered at the Large Hadron Collider, a pivotal discovery made simultaneously by two large multipurpose experiments, ATLAS and CMS. It was announced on July 4, 2012 at CERN. At that time, the new scalar boson was observed primarily in two rare decay channels, which offered the cleanest signal. The decay was seen in a pair of photons, which involved a purely quantum virtual process, and the direct decay into a pair of Z bosons, the carriers of the neutral-weak interaction. The discovery of the Higgs boson back then may have completed the Standard Model, but it wasn't the end of research on this elusive particle. Since 2012, key findings have included confirmation of the Higgs boson's decay according to theory. This examination of the elusive particle will intensify during the third run of the LHC, particularly when the accelerator's high luminosity upgrade is completed in 2029. This will allow the LHC to conduct more collisions, giving scientists more opportunities to observe exotic physics, including phenomena beyond the Standard Model. CERN has estimated that as the accelerator is upgraded each year, it will produce 15 million of these particles compared to the 3 million Higgs bosons generated by the LHC in 2017. This may be crucial for detecting other types of Higgs bosons, speculated to extend beyond the Standard Model of particle physics. Predictions suggest up to 5 different kinds of Higgs bosons may exist, potentially produced less frequently than the primary Higgs boson. Even before the upgrades, researchers had already found strong evidence for a magnetic Higgs boson. But why is the Higgs boson so important? The Higgs field played a crucial and definitive role in the moments following the birth of the universe. It determines the physical nature of the vacuum that permeates our spacetime. It is the reason matter and interactions exist as we know them, and it is responsible for the mass of all known elementary particles. Without the Higgs field, and thus without the Higgs boson, there would be no atomic elements, no stars, and no life in this universe. The God particle. Why is the Higgs boson called the God particle? The moniker, God particle, was popularized after its discovery, thanks to mainstream media. Its origin is mostly attributed to Nobel Prize-winning physicist Leon Lederman, who referred to the Higgs boson in frustration as the goddamn particle, because of how difficult it was to detect. According to Business Insider, when Lederman wrote a book on the Higgs boson in the 1990s, he wanted to call it the goddamn particle, but publishers refused and changed it to the God particle. This was the start of a controversial association with the Standard Model. The association of the Higgs boson with the God particle moniker has remained contentious among scientists. Many physicists dislike the term as it overstates the particle's significance in religious or supernatural contexts, when in reality, its discovery is purely scientific.